Good. Okay, so what do you think? Is this one going to work or not? Yes, no? So, okay, whatever, it's literacy test. You're like waiting for a chance to answer a question. It's like, I just saw the answer. I could go for it. Except, what if there's a game within a game? And I actually put that on there and Coach Devine to ask me right at that point to see if I could trip someone up. So now you have to think, well, wait a sec. Could he actually have said that? Is he that organized? I don't know. So what do you think? Is it going to fit or not? You think no? I see you shaking your head. What's wrong? It won't fit. Why not? Right? Yeah. You're right. Yeah. So it's too much. So if we look at it, it basically winds up when you need 9 inputs per ALM. You can actually do each LUT is okay. The individual LUTs, each of them can do a 2-to-1 mux. You got 4 of them, 4 LUTs, that would all be fine. But when you add up all the inputs, I basically need 4 inputs to do this selection, another 4 inputs for the upper bit, and then I need my actual select control signal. So it's 9, it won't work. Okay, so we can map a fair amount of logic down front of our adder, but it's not infinite. And here we ran it, and we usually run out of inputs before we run out of sort of LUT capacity. Yeah. It's because I only wrote 1 bit, okay, because I got bored. But I'm basically doing this for a multi-word, like a multi-bit expression. Like say it's a 32-bit add. So then every ALM needs to do 2 bits worth of addition. I probably should have put a ... in the same thing for bit 1. Does that make sense? So I'm really selecting between 2 data words, adding them together. And you're right, if it was a 1-bit adder, it would be fine. But even though I didn't write it down here, in my mind, it's a multi-bit adder. So perhaps it's an unanswerable question, but you still answered it well. Thank you. Okay. So the CAD tool basically checks, will this fit in the LUTs? It checks whether it fits in the ALM. And there's one more check. So you also have to check, will it fit in the logic block? So let's see, we looked at this case. We said this one would fit fine, right? We could take some number A, and we could choose either B or C and add them together. And let's say they're all 32 bits. So if they're all 32 bits, we can fit 20 bits of carry in a logic block, right? 2 per ALM, and in all recent Intel chips, there are 10 ALMs in a logic block. So we need to get 20 bits of this in one logic block. So you need to work out, well, how many inputs do we have per bit? And then I need to make 20 bits of that fit in a logic block. And all of that, the carry in, I'm not worried about. Okay. Well, if this was from the previous logic block, it doesn't count in my number of regular inputs. But I do care about the number of regular inputs I can bring in from the general routing. And we saw when we were architecting logic blocks, more inputs means more muxing, it's more expensive. We actually try not to have too many. So in Stratix, so if we expand this out, for every bit, we get this pattern. We get 3 inputs per bit of this 32-bit word. Now, we're not going to fit all 32 bits into one logic block, but we will fit 20. So if we add up how many inputs we have 20 bits, and each of them is taking 3 inputs, right? A, B, and C. And then we also wind up with 1 input for control, right? So we need a select signal that actually says, are we going to use A or B? But we only have to bring that in once. That's 61 per logic block. And in Stratix 4, the number of inputs that Intel actually built per logic block is 52. So 61 is more. It's not going to work. And in all the recent logic blocks, 61 is too high. Okay, it's more than you would normally have going into a logic block. What would normally happen is the CAD tool just wouldn't do this. Okay, so if you have a bunch of lookup tables that all use lots of inputs, they're not related, Cordis would just never put all of those lookup tables together in one logic block. It just says that's illegal, go find something else. The difference here is we have this dedicated routing, so we can't take this apart, right? Like these adders are constrained. All of these, if we have to put all these adder bits together, the synthesis tool could choose not to use the LUTs. Okay, so it could just say, fine, we'll do a LUT out here. It loses efficiency, that'll be okay. But it doesn't have the choice of, just kind of doing a few bits here and some other logic, which is what it would do normally, right? It just would not try to put so much logic with so many inputs in one logic block. It would go find something else to put in there. But the dedicated routing is constraining us. But it does have the option of just don't use the lookup table so much, and you'll lose efficiency. We'll have to go in some other logic block. But it's a bit disappointing because you kind of almost could do this, but we just don't have enough inputs. So one fix is just purely the CAD tool. Just say, don't do this, right? If this is illegal, don't put part of this in the LUT, put it in the logic block next to it, and that'll work. You'll just lose some efficiency. Intel did something that's actually a bit more clever. So I know Isidore knows the answer to this, but can you think of like another way that you could fix this that's relatively cheap? It's a change to the architecture. And so one way you could fix it is make more inputs, right? There's 52 inputs, but that's expensive. Okay, so I can make it 61. 61 is going to be kind of marginal. If you actually use all the inputs to a logic block, it's a difficult routing problem. If you don't have any spare inputs, it means it's kind of very easy to get blocked, right? If you can't get one thing to the right spot, you fail. So it's actually the CAD tools don't like to use all the inputs. So while you have 52 inputs here, the CAD tool will prefer not to use 52. It would be much happier at 45 or less. So we could increase this to 61, or probably we'd have to increase it to 70, but that's expensive, right? All those routing muxes are a lot. Is there anything else we could do that's cheaper? Yeah, so we could use 2 logic blocks. And I guess I basically told you the CAD tool with no changes could just take one of these LUTs and say, don't use this, just make it a feed through and do it out here. So it could do that. Is there any change I could make to the architecture, though, that would let the CAD tool use all these LUTs? Because we could almost use them. But it has to be cheaper than just adding lots of inputs. If you can't see it, it's fine. It's kind of a trick, but I find it an interesting trick. So Isidore, I know you know this one. So what would you do? Okay, so Isidore doesn't know this one either anymore. So we're going backwards because you know this one before. So yeah, what do you think? Yeah, so that's what I mean by the CAD tool could just do the mux operation in a different logic block. So that would work. It could do that. It does mean I got to use up another logic block. So there's a cost, but if I can't come up with anything else, that's exactly what the CAD tool should do. Yeah.
Can we do time but in the routing center?
Oh, yeah, that could work. Although that is a radical idea, right? You could do that, but you change the architecture in a big way. Yeah. You could do that. No, those are not bad ideas, but they're fairly radical. So it's not what Intel did, because it changes the architecture in a big way, and you probably try to use it in all sorts of places. So let me show you what they did. So basically, the reason why you can't do this kind of what looks like a very nice mapping is you can't do it for the whole chain. You're going to run out of inputs to the logic block, and the chain is all dedicated routing. So you also can't split it apart. So they basically put in just a little bit more configurability to let you split the chain in the middle. So normally the chain in an FPGA would go, straight through all of the adders, and then it goes straight into the adders in the next logic block. And so you just get as long a chain as you need. And all the routing is completely dedicated. So all that routing is really fast, right? It's just a wire with no configurability at all. So what Intel did is they basically said, well, if I could just 10 bits, right? 10 bits of arithmetic is for sure always going to fit, right? Even if I make maximum use of these ALMs, use lots of inputs, I wouldn't use all my inputs. I'd still have some inputs left. So they basically built what they called an early exit carry chain. They have the option to just take the carry out of the 10th bit and send it to the next logic block. These other 5 ALMs would just not use their adders. Okay, they would just do some regular logic. And what have they added? They've added a 2-to-1 mux. So there's a little bit of area, a little bit of delay, but not much. You get 1 2-to-1 mux for every 10 to 20 bits of carry. So it's a very small delay penalty. It's a very small area penalty, and it makes it easier to use this structure. Oops, see if I can get rid of this thing. It's getting worse, sorry. Okay. Oh, I unshared the screen. All right, let's see what I got here. Okay, so this basically lets them put even very complicated carry chains in half the logic block and then put other stuff, less complicated stuff that doesn't need too many inputs in the other half. It's pretty common that carry chains aren't that complicated. Maybe they're just doing addition or subtraction. In those cases, use all 20 bits. So it was a cheap place to add configurability, make this more usable. Okay, so that's it for arithmetic and logic blocks. Any questions on that? Yeah. Like inside the logic block? As one of Andrew Boutros's papers from his master's degree, actually, that's one of the things that he tried in it. He called them, so there's a paper on that if you go look for it. It's sometimes called like shadow multipliers. The idea is you put like a small multiplier in that gets to reuse the routing ports. And now you become quite good at small multiplication. So it is a feasible thing, right? You could do it. Multipliers they are bigger, even small multipliers are significantly bigger than an adder. And they're common, but not as common as addition. So it's a reasonable thing to try, but it's not clear it's a complete win. If you need tons and tons of multiplies, which you do need in machine learning, it's probably a good idea. If you are doing more general logic circuits, then it's probably not a good idea. Does that make sense? But yeah, it's a good thought. Okay, we're done with logic blocks. We're going to talk about RAM architecture. And this is very relevant to the assignment you're doing. So if you're kind of going, like 2.5 hours is a long time, I can only pay attention to part of the class, I recommend you pay attention to this part, right? Feel free to pay attention to all of it, but no penalty for that. But if you gotta ration your attention, bring it on now. Okay. Okay, so memory architecture is important. So the single biggest thing, again, the IOs are big on an FPGA, but let's just talk about the core. Single biggest thing on the FPGA is the programmable routing, if we neglect the IOs. Then the logic blocks and the RAM blocks. Okay, so RAM blocks are about 20% of the area of, again, the core of the FPGA. The IO area is kind of hard to say. For a big chip, it's not that much. For a small chip, it could be most of it. So this is big, right? After we look at logic and routing, this is the next thing to look at. What does it do? A lot of different things. So circuits need RAM for many, many reasons. So one is FIFOs. You've seen already when we do these data flow or latency and sensitive architectures, they use FIFOs all over the place. So we want FIFOs. They also use it for scratchpad RAM. So scratchpad RAM, little bits of RAM, they're just storing data I need. So what do we need that for? Packets. So FPGAs do a lot of communications, so you need to store the packets. Often the packet body is stored off chip in DRAM, but the headers are commonly stored on chip. And even the header is smaller than the body of a packet, but it still adds up. So you need a fair amount of storage for that. Constants for programs. If we have FIR filters and convolutions, we need to store the coefficients somewhere. Okay, so we often use soft processors in part of our design, either regular soft processors like RISC-V or Neos or Microblaze, or really weird ones like the NPU soft processor that we saw earlier that was being used for deep learning. But they all need to store their program. So that's another reason. We can control hardware with basically little instruction memories. So we saw that was another design style. Make a custom data path, but don't control it with a finite state machine. Make a little instruction memory. Register files. As soon as we use anything that looks like a processor, it's going to have register files, and those go in memory as well. And even things that are very unusual processors can have register files. Okay, so before we build anything hard on an FPGA, like RAM blocks, we should ask, well, do we need them, right? We want this chip to be as flexible as possible. It's most flexible if it doesn't have too many hard blocks. So maybe we're done. We already have registers and logic, and we can build RAM out of that. So let's see how efficient that is. Okay, so if we build our RAM out of regular logic, and the earliest FPGAs did this, there's some significant negatives, is it wastes most of the functionality of our basic logic element, right? We've got a LUT and a register, and we're getting basically the register to do 1 bit of storage. So we're kind of wasting most of the functionality. We need a whole bunch of memory bits, so we're using our registers for that. And then a RAM isn't just memory bits, it's muxing and decoding to choose what memory bits are you writing and are you reading. That muxing and decoding actually gets pretty big. So I'm going to show you in a minute how big. So there's some pretty significant downsides to doing this. The positive is we'll get exactly what the end user needs. Okay, so if you need a RAM that is like 8 bits wide and like 73 words, and it needs 1 read port and 2 write ports, you can build that, right? You'll build it out of the logic and they'll get exactly what they asked for. So that's the benefit. Okay, so whose money is on, we should just build it out of logic, registers and LUTs, and who thinks we need to put block RAMs in? So who thinks registers and LUTs? Isidore's in for registers and LUTs, same with Alex, okay? Who thinks no, Isidore and Alex have gone mad? We need to have block RAM. Realizing that every modern FPGA has block RAM. So Isidore and Alex have arrayed themselves against the entire industry. So so I think most people are probably going, okay, I'm not with them on this one, right? So yeah, so it's too expensive. So we take just one example. So let's take a 256 word, so we call that depth, by 32-bit wide. So your word size is 32 bits, and you got 256 words. So maybe this is a register file, 256 32-bit registers. How big is that if we build it out of registers and LUTs? Well, the first thing I need to have enough storage. So I need 32 times 256 registers. Okay, so that's 8,000, over 8,000 registers. I also need to decide, when you send me the write address, you're going to send me an 8-bit write address. I need to decode that and decide which one of these 256 words gets written. That's an 8 to 256 decoder, which is actually a reasonably large thing. When I do a read, you're going to send me an 8-bit read address, and it's going to choose which one of these 256 words I read out. Okay, that is a 256 to 1 mux, and I need to have 32 of them, 1 for every single bit in this word. Okay, so that's big. So if I add this all up, that takes about 6,000 Intel ALMs, which is actually, if you just took the registers, you'd go, maybe it'll fit in 1,000 if I have 4 registers per ALM. But it actually takes maybe 4,000 if I have 2 registers per ALM. It's actually even worse. So 6,000 ALMs, which sounds like a lot, right? Like that's a fair amount of logic. So let's compare that to how big is it if I just build a RAM. And the RAM that I need for this is 8 kilobytes, or 8 kilobits, sorry. So I need an 8 kilobit RAM, and it has to be capable of providing a 32-bit word. And in Stratix 4, Altair actually has a 9 kilobit RAM. So it's actually a little bit bigger even than I need for this. It basically has parity bits. So it's a little bit bigger than what I need. It can do up to 36 bits wide. So it has more than enough bits. It has more than enough width. Its area has been published, okay? And one of the benefits of being in a company is area was published by me. So when I was co-supervising a student at U of T, and he needed this number, so I consulted myself about whether it was okay to give him the number, and I gave him the number. And since then, lots of people have referred to this. It's actually hard to get numbers like this out of companies, including me. So it's actually it's useful. So the area of this block, including of all of the routing ports, its interface to the routing, is 28 ALMs. So I just divide this. It's a 200x density improvement. So this is enormous. Like, this density improvement is so big it swamps any issues like, I kind of wasted a bit of this RAM. I only needed 8 kilobits and I used 9. Who cares? The 9 kilobit RAM, including all this interface to the routing, is 200 times smaller than building this out of registers and LUTs. So you need to have block RAM. Does that make sense? So that decision is settled. Okay, so now we know we need to have block RAM, but we have to decide what to build. So before we know what does, every person who uses this FPGA will have to live with the decisions that the FPGA architects makes here. So we have to decide what physical RAM blocks we build. And the decisions here are, well, how many bits? What's the width of the ports? Okay, so the area of a RAM block is not just how many bits we put in it. That's clearly part of it. If it provides wider data words, that actually leads to more peripheral circuitry and more routing ports. And I'll show you that in a minute. But basically, making it capable of serving up wider data words costs more. So we have to choose that. And then we also have to choose how many ports. Okay, so the simplest RAM that we can build is what's called a single port RAM. Okay, so it's got one read/write port. So on a given clock cycle, I could do a read or I could do a write, but I can't do both. Okay, that's a single port RAM. I might want to get more done in a clock cycle. So I can build a RAM that has one read port and one write port. So now I can do both a read and a write in a single cycle. Or I can build a RAM that has 2 read-write ports. So now I could do 1 read, 1 write. I could do 2 reads in a cycle, or I could do 2 writes in a cycle. Any one of those things will work. So it's a bit more flexible. But you'll see that as we do this, as we make the RAM more complicated, yes, we can do more with it, but its area also goes up. So it's a trade-off study here. What's the right place to go? Another question, so this is all about block RAMs, dedicated blocks of RAM that we're going to hook up to the programmable routing. The other thing that we can look at is we have these lookup tables all over this chip. And the lookup tables are basically a ROM, right? You preloaded in memory bits and you read them out. If we could somehow rewrite those bits, then this actually becomes a little RAM. Okay, it's usually called LUT RAM. And depending on how costly it is for us to make our LUTs more general so we can do this, maybe this is a good idea, maybe it's a bad idea. So that's the space you're actually asked to explore in assignment 2. Okay, so everybody with me on what is the space? Cool. Okay, so what's the RAM mapping problem? So designers don't generally they don't care what's on the chip, right? They want to describe their circuit and the chip is something they bought, right? They should implement the circuit. So designers normally ask for what are called logical RAMs. So basically they instantiate IP or they just code HDL or they write HLS code that either explicitly ask for some RAMs or implicitly ask for RAMs, but those are all logical. Okay, so let's say, for example, that I write some Verilog and it has an array of 2048 words and they're 32 bits wide and I need 2 read ports. So I'm doing 2 reads in one cycle and 1 write port. So in one cycle, I do 2 reads to different addresses and I write to a 3rd address. So this is just an example of I might need that. Okay, so I put that in my design. We're going to go through an example of how do we map that to physical RAMs. So I don't actually have this on my FPGA. What my FPGA has is it has a whole bunch of 8 kilobit RAMs. They can do 1024 words, and those words are 8 bits wide. Okay, but I have a lot of these, potentially thousands of them on my chip. And each of these physical RAMs, it can't do this, 2 read and 1 write. It has 1 read port and 1 write port. Okay, so the RAM mapping problem it's a mapping problem. It's to go from this logical RAM request to how do I actually do that? What physical RAMs would I use, and is there any extra logic that I need to connect up as well? So we want to do this map. Okay, so how would you map this? And in assignment 2, you don't have to write like the HDL. What you have to do is count. You have to say, I need this many of this kind of RAM, and I'm going to need this extra logic. So you need to know how would I build this, but you don't have to actually write out HDL that builds it. You just need to output like a count if I needed this. So how are we going to map this? Let me break that down into I have a nice picture. Okay, so before I ask that question again, this just graphically shows what I said. I want this big logical memory, 32-bit words, 2048 of them, 2 read ports, 1 write port, and I have a whole bunch of these physical RAMs, which are smaller. They only have 1 read and 1 write port. They only have 1,000 words, and they're only 8 bits wide. So clearly, I need more than one of these physical RAMs. It's not going to work otherwise. But how do I do this? How do I combine them? So yeah, Isidore, what do you think?
If we have where here it's asking for 2 read ports and 1 write port, and the physical RAM only has 1 read port and 1 write port.
Yeah.
We make basically copies for every bit. We can write out both, and then the other read ports from each of those.
So you're jumping way ahead. So you're going to answer all my questions now, right? So we're going to answer this piece by piece. So it's a good question, but you're jumping to the. So yeah, I'm gonna. So I guess the short answer is yes. Okay, that's the short answer to your question. But let's build it up piece by piece. The other thing I should say is in the actual assignment too, you won't get any RAMs that are more than 2 port. Okay, so you won't get like a 2 read and 1 write because it's just too messy. Okay, and it's not the most common. So all the RAMs you're going to get will have at most 2 ports. But just because I know you can take it, we're going to do the more general case where you have more ports than that, because it does exist actually too. It's just we're not doing it in assignment 2. Okay, so I'm going to ask this a bit by bit. Let me see if I move this out of the way. Let's see. Okay, so first step. So I'm going to guide the question. The first thing we need to do is I want to basically get the right width. Okay, so I've got this big RAM, 2048 words, and yeah, 2 read ports, 1 write port. I'm trying to implement it, and I only have these 8 kilobit RAMs that can do 8 bits each, or sorry, 1,000 words and 8 bits wide. So first thing I want to do is I want to cover kind of the upper part of this logical RAM, and I can do that by making a wide enough word. So how do I map just that half? I want to start by just mapping that half of this logical RAM to physical RAMs, because this is kind of the easiest mapping. Isidore, what do you think? So that's a very good answer. Your answers are always so good. You go like 2-3 slides ahead. So it's very good. But so yeah, so you're right. So this is kind of the easiest way to combine physical RAMs to make a bigger logical RAMs. You put them in parallel, exactly as Isidore said. I wire up the read address to all of these RAMs. I wire up the write address to all of these RAMs. Each of them provides 8 bits of the word. So if I concatenate that all together, I've got a 32-bit word, right, for both my write path and my read path. So it sounds good. Yes, that's it for the kind of matching the width. Okay, you can just parallel them. And I didn't need any extra logic. So that's good. This is a very efficient way to combine them. Okay, that only covered the top half of the RAM. I now need to cover the bottom half. And Isidore actually said how to do that too. Okay, so to combine the RAMs to match depth, well, I need more physical RAMs, right? I had 4 that together made up the top half of this logical RAM. I need another 4 that together are going to make up the bottom half. Okay, I'm hooking up my read address and my write address are being hooked up to all of these RAMs again. Okay, at least now these RAMs only have 1,000 words. So I'm hooking up 11 bits of read and write address here because I've got 2048 words. Okay, so there's one address bit that I haven't done anything with yet. But the bottom 10, I just hook up to everything. Okay, so I'm showing the write path in blue. Okay, so I've got a write address that I've hooked up to all of the RAMs, bottom 10 bits of the write address. And I've taken I also need my write data. So I've got a 32-bit write data, that's my word. and I'm hooking up 8 bits to each one of these RAMs, and I also hook up 8 bits to each one of these RAMs. So it kind of goes to both groups of memory, and it sends 8 bits to each one of the physical RAMs in that group to make up the 32-bit word. So my first question is my write path okay? My write path is blue. Does everybody like my write path? Anything you'd add? It's mostly okay, but is it complete? Isidore, I think, is concerned about it. Alex, what do you think? Yeah, so what's wrong with it? It's almost right, but there is a problem. Like basically, I've wired my bottom 10 bits of my write address up to everybody. I've wired up my data bus properly, 8 bits to each. When I send in a write, I write right now into both arrays. Okay, so I write a word here and a word there. Not what I want. I actually basically, therefore, I can store the same data twice, right? 1,000 words of data, but I store it twice. So it's not quite what I want. What do I need to do to fix this? Yeah, so I need to use my last address bit on the right side as a write enable. And all of these physical RAMs do have a write enable, okay? So I hook up the true to one of them, I hook up the complement to the other, and now either the top or the bottom group of RAMs will be activated on a given write, and this now behaves properly as a 2048 word memory, at least for the write path. So, and I didn't have to add much logic. So far, what logic did I add? I added one inverter. So in your RAM mapping, you're going to count that. When you do this, you go, I added one LUT, okay? It's so small that, in fact, if you didn't count it, it might be round off and nobody notices, but you did add one LUT, okay? Okay, what about the read path? So the read path's in red. I've hooked up my read address, 10 bits of it, to both the bottom and the top, and I just have these arrows coming out. So I'm getting 8 bits of data from each of these RAMs. That makes a 32-bit word. 8 bits of data from each of these RAMs, another 32-bit word. I did not actually connect them to my output. So notice they don't actually make it to my read data, which should go out. So I appear to be missing something. The fact that there's a white spot in here indicates there might be something missing. What do I need to do here? So what's missing? So Isidore, what do I need to do? Right. So I'm almost there, but I basically now need to mux out which of these was I looking at. So I need to look at the top read address. And so I didn't actually draw this, but it's going to be controlled by the top read address. So it'll be like read address 1 of 10. Okay. And now it's going to select which of these two do I want. This actually adds up more. So how many lookup tables do I need to implement that mux? 2? So take a look at the data path width. So close. Yeah, what do you think? Well, this is actually just a 2-to-1 mux, okay? Because it's just so it's actually important to think about what is this. So it has 32 bits of data coming in. It's 32-bit wide buses, but I've got one select signal. I'm just checking for the bit 0 of here and bit 0 of here. I'm going to pick one or the other. Bit 1 of here and bit 1 of here, I'm going to pick one or the other. So this is actually 32 muxes. Each of them is 2-to-1. Can I fit a 2-to-1 mux in a 6 LUT? Yes, because 3 inputs is less than 6. So, and if you remember that, you're still following. So it's just that's the beauty of LUTs, right? It's counting, and you only have to count to about 6. So, yeah. Yeah, and in the assignment 2, we allow up to 16-to-1 muxing. After 16-to-1, we just say it's going to be too slow. Don't do it. So you need to have like a little table, which you can work out, or if you can't figure it out, post on Piazza and I'll tell you. Basically, up to a 4-to-1 mux fits in a 6 LUT, right? 4 data inputs and 2 select inputs. After that, you're going to need to basically have a second level of muxing, okay? And you can work out how many LUTs it is without too much effort, or if you get confused, just post on Piazza. But that is something you'll need in order to evaluate the area of your mapping solutions. If you get completely confused, the checker will also tell you the area. So it is like it helps you. Okay, so this is okay. So once we put this mux in, it works. Basically the area, but we added actually 32 LUTs here. Okay, so we added 1 for the inverter, 32 for the muxing. So it's not catastrophic, but it actually does add up when we do this. When we're combining, depth-wise combining RAM, we get extra logic. When we do it in parallel, we don't get extra logic. Okay, so it is okay. Let me ask you one other question, which you don't have to do an assignment too. So you can, if you're kind of going, I'm focused on the assignment, you can tune out for the next 45 seconds. I would assert this is not as power optimized as it could be. And RAM power actually is significant on an FPGA. The power usually follows the area reasonably closely. So the largest power goes to the programmable routing. Logic is often second, but RAM is also often second. Okay, so RAM power is significant. Is there anything here that's wasteful of power? The thing that hurts in a RAM is basically, we showed that for most logic, you have this toggle rate. You know, it's like you're charging and discharging capacitance. The way we're going to talk about how a RAM works internally in a minute, but basically a RAM, whenever you access it, it consumes memory. Okay, because of the way it works. There's a pre-charge and an evaluate cycle. It doesn't actually matter if you charge and evaluate cycle. It doesn't actually matter if it's RAM to do a read, it consumes data. It doesn't actually really matter what the read data turns out to be. If you ask it to do a write, it consumes power. It doesn't really matter what you write. Which is a little different than the rest of your logic, where what mattered is whether it's changing state or not. Anyway, so we would like to not.
What do you think? What are we wasting? Yeah, well, I think one thing you could do is you could put them on.
Yeah. So these RAMs, you don't need it for functionality. I don't think I actually drew this on the slide. Yeah, okay, I guess I didn't. They have also a read enable. Okay, and you don't need the read enable for functionality because reading a RAM is always a safe operation. But in this architecture, we're actually reading 2 words out, one from here, one from there, and then we throw one of them away. Okay, so if we hooked up the top address bit to the read enable of this and it's inverse to that, we'll actually cut the amount of reading that we do in half. And that's actually worth doing. And it's, in this case, pretty much free. There are actually some other things that you can do. So at the end of this, towards the end of this section, I'll cite a couple papers if you're interested. You can do more than that, but they start causing some area delay trade-offs. You don't have to do it for assignment 2. Assignment 2, you're focused just on area. But when you actually map for RAM, there are some alternative mappings you can choose that actually will save additional power, but cost some extra logic. But anyway, the read enable one is an easy one. Okay, so we're almost done, but what we just built, it has, let's go back and look at it. We have the right number of words. We have the right word width, but we don't actually have the right number of ports. What we have right now is we built 1 read address, 1 write address, and we don't have that second read address. So, and Isidore actually asked about this before. He said, well, if we need another read address like this, and these RAMs only have 1 read and 1 write port, do we just have to duplicate the whole thing? And yes, you duplicate the whole thing. It gets really painful. So to make that second read port, you take that whole big structure and you basically make 2 copies of it. Both of them use the same write port. So we're always writing the same data twice. We write it into 2 different groups of RAMs. The whole reason to write it into 2 different groups of RAMs is that we have 1 read port can be reading 1 RAM, the other read port can be reading from the other RAMs. So going to if you build physical RAMs that have a smaller number of ports and then your design needs a larger number of ports, it does get expensive very fast. And there actually is a whole sequence of papers on this where people try to come up with tricks to make it less expensive. This is what you have to do for read. I'm not going to draw it. If you actually needed more write ports, it's worse. Okay, so this looks bad, but write ports are even harder. And there's a whole literature around that. How do I get highly ported memories on an FPGA when I'm not an FPGA architect? So I can't just change the chip. I just have to use what's there. Any questions on this? So yeah, it gets expensive. Don't use tons of ports in your logic. So. So hold that thought. So I'm going to ask that in a second. So let's see. Yeah, I'll take a break in a few minutes, but let's go for another few minutes. Okay, so I guess observations from this, we can combine RAMs to make a wider RAM without any extra logic. So in your RAM mapper, that's kind of the nicest way to combine things, right? Just put them in parallel. We can combine RAMs to make deeper RAMs, more words, but it takes extra logic. We need to decode the upper address bits to decide which RAM to enable when we're writing. That costs a little bit, but not too much. And then we need to build some muxes for every single bit on the read output so that we select the right data. That's more expensive, and it's because it's a whole data bus, right? Logical RAMs that need more ports than you have on the physical RAMs, you can build them, but they are expensive. So we basically needed 2 read and 1 write port, but we had 1 read and 1 write port on our physical RAMs, and that actually made us duplicate the whole thing. So to get that second read port, we made the cost double. Is there anything else we could do? So one thing we could do is we could change the FPGA, but like without doing that, is there anything we could do? What do you think?
So I'm gonna because the RAM is hard, can't you just make the RAM run double frequency and double pump it?
Yeah, so you can double pump it. That is done sometimes. Okay, so if exactly what you just said. So if the physical RAMs can be pretty fast. So in recent FPGAs, the block RAMs can usually cycle about 1 gigahertz. It's a challenge to make your logic run at 1 gigahertz. Therefore, you might go 500 megahertz is good enough. I'm going to actually do 2 accesses per clock cycle, and I need a little bit of circuitry now to basically do a little multiplexing. But it's like one of our programming models of like time domain multiplexing. So you can time domain multiplex the RAMs to get more ports. And the faster they are compared to your logic, the more beneficial that is. Yeah. So that's a good question. So you can do it in soft logic. Some vendors put a limited amount of hard logic to allow you to do it more easily. So there's both, I guess. The more common thing is it's in soft logic because you can do that on any FPGA. But I'll give you an example where there's a little bit of hard logic to do this in one recent FPGA. Well, so that's a good question. So you're basically saying, well, even that little bit of soft logic, can you run that at 1 gigahertz? You can run little bits of soft logic that's carefully crafted at 1 gigahertz. So you can build the time domain multiplexing circuitry right around that RAM, and it can keep up. You might have to babysit it a little bit, like be pretty careful, and you need the tools to do a good job. And if they don't, you might have to go in and fine tune things, but it is possible for it to keep up. So that's a good question. Yeah. 2 writes and 1 read. So yeah. Okay, so 2 writes. This is where there is a whole literature, some of it by Professor Greg Stuffen from this department, published a bunch of papers on this. How do we do more write ports? 2 writes is painful. The basic, most efficient technique is, well, one of them is called the live value table. And what it does is it basically builds in just logic. Okay, so it goes back to, I'm going to build this in logic where I can build anything. It builds who has the most recent value for this word. And it builds essentially a small, very highly multi-ported RAM in logic and registers that identifies which RAM has the latest copy. Okay, and then it goes and accesses that RAM to get the whole data word. It's fairly expensive. But because they don't, the live value table basically makes it a much smaller table of just where is the most recently written thing. And that's put in logic with essentially lots of muxing and decoding, so it can have many, many ports. And then it looks up the full data words in the appropriate physical RAMs. Does that answer your question? So you're channeling George. You're now you're now an avatar for George, right? So you're part of the metaverse now. Okay, sounds good. Okay, but yeah, it's a good question about time domain multiplexing. And let's see. Okay, let's take a break for 9 minutes to 5:30, and then we'll talk about choosing a physical RAM architecture, which is your second part of assignment 3. That Amin has actually got all the results from the assignment 2 contest, but I didn't have time to fully process them or get them slides. So next week I will announce them and give out prizes. And thank you for getting them ready, Amin, so I didn't keep up my part of the pipeline. So. Okay, so we're gonna go in again. Okay, guys. Now you have to pay attention to me now. So, okay, so we now move on to like this. You guys are gonna have to take it offline until the break. So you have to take it offline until the break. Okay. So okay, so let's move on to the next question of how do we choose a physical RAM architecture? Okay, so in order to analyze this, you have to know something about how RAMs are built. How many people know how SRAMs are built? So how many people don't know how SRAMs are built? Which is fine, okay? And then other people are kind of like, I'm not sure. Maybe I know, maybe I don't know. Okay, so for those who know how they're built, this will be a review, but it's important if you're going to try to architect this to know what's happening. Okay, so if you build a single port SRAM, this is the standard way you build it, right? So you use 6 transistors. You have back-to-back inverters that are your storage cell. You have 2 access transistors. When you activate the word line, so it goes to a logic high, these access transistors turn on, and they connect you to a bit line and its complement. If you look inside these inverters, there's a pull up and a pull down. The pull ups are built to be weak. And what that means is that if I put a logic 0, well, I will put a logic 0 on one of these, say it's on the bit line bar, which means I'm trying to write a logic 1. This access transistor is more powerful than the pull up inside this inverter. So it'll overpower that pull up. This will be pulled low. Once that goes low, the latch will go to a stable state. If I wanted to write the opposite, well, I just put the opposite pattern on, a 0 and a 1, and it's the pull down again that wins. This 0 will go through this access transistor and it'll overpower the pull up here. Okay, so that's how it works. It's actually, SRAMs are not scaling as well as they once did. It turns out at really low voltages, it's difficult to do this with really small transistors. So you'd like to make these transistors really small because you want to make a lot of SRAMs. But you can't make them infinitely small because you need this to be more powerful than the pull-up inside here. So that's actually producing some challenges in scaling SRAM in really advanced process nodes. But that's a digression. That's a challenge for those working on process. So it takes us 6 transistors to build an SRAM cell. And this is what's called a single port SRAM cell. It's a single port because, well, I have one word line and I have one set of bit lines. Okay, so I can read one value, I can read out of this or I can write to it, but I can't do both. Okay, that's the cell. To make an SRAM array, well, first I make an array of these. Okay, so this is my rows are my words, my columns are data bits within that, and I need to build some peripheral circuitry. So I build a row decoder. So I send in an address, and the decoder decodes all possible combinations. So if I sent in an address that was like 00001, word line 1 would go high, and this whole set of cells would be enabled, right? They'd be connected to their bit lines. And all of their bit lines are going like this, okay? So that's like one of these cells would be here, and its bit lines are now connected to a sense amp, okay? So that's what sense amp 0 means. So what is a sense amp? People know what that is? Alex, what's a sense amp? Yeah. Yeah, so that's a great description. So it's a clocked differential amplifier. They're always clocked because they basically you do exactly what you just said. I'm about to do the read, So I equalize my bit lines, both of them to VDD over 2. I enable my sense amp. Well, I wait a little while for the word line goes high, and therefore this SRAM cell, based on its state, will start pulling one bit line low and one bit line high. You give it a little while to develop enough voltage, and it needs about 30 millivolts, okay? Then you activate the sense amp, and it basically detects which way did it go, up or down, and it outputs a 1 or a 0. So the reason you do this is these SRAM cells are small, they are weak, and the bit lines are long, they're highly capacitive. So if you just waited, if you activated the word line and just waited long enough, eventually your one of your bit lines would go to 0 and one would go to 1, right? But it'll take a long time because you've got a little set of transistors driving a big capacitance. So you don't wait that long. You have this sense amp, as soon as it can tell the difference, it outputs the value. So yeah, that's your sense amp. So let's talk about that was the read. That's what I just told you. The write is similar. Basically, this is the write driver. So the write driver, you send in what value am I trying to write for every one of the bits in your word. Again, you decode the address, you activate one word line, and then these drivers are strong. So they strongly pull bit line up and bit line bar down, or vice versa, and it's enough to flip the cells. Okay, so the cell in that selected word. Okay, so that's how this whole thing works. So the reason you need to have this mental model is it tells you where the area goes. So I'm going to give you a simple area model that's actually fit to real data. So the area model is realistic, but the shape of it comes from what are all these little bits of circuitry. Okay, so I want to build a dual port SRAM. The first thing I have to do, I still just need one storage cell. So the heart of my SRAM is always these back-to-back inverters that form a latch. And I still have these blue lines, which is my word line, my 2 bit lines, like my bit line bar, keep all that. I want another ability to read or write this cell in the same clock cycle. I basically duplicate my access transistors. So I get a new pair of access transistors, I get a new bit line and bit line bar, and I get a new word line that controls these new access transistors. So I have my A port, and I added my B port. So what did it cost me? Instead of 6 transistors per cell, I get 8 transistors per cell. And instead of one, and if I'm metal limited, instead of 1 word line and 2 bit lines, I get 2 word lines and 4 bit lines. So if I'm transistor limited, it's going to increase my area by about 1.33. If I'm metal limited, it'll be a little worse than that. Okay, when you put that in the array, okay, so my basic cells are now bigger. I make a big array of them. I have everything I used to have, right? I need a decoder for my port A. I need my write drivers and my sense amps for port A. And I just have to do that again. I need to have a decoder for port B, and I need to have sense amps and write drivers for port B. So all my peripheral circuitry basically gets doubled, and my SRAM array gets maybe 33% bigger. Does that make sense? So we can build multi-ported RAMs, but they do get more expensive. So we'd rather not build like a lot of physical ports if nobody's going to use them. Okay, so what are some of the trade-offs here? So larger RAMs are more efficient per bit. They're more efficient per bit because they basically amortize this peripheral circuitry. Okay. And I'm giving you, I give you in the handout the actual numbers for this. But basically, your area model is there's a strong dependency on the bit count, right? You add more bits, that big array gets bigger. But there's also a dependency on basically the square root of bits, because that's your peripheral circuitry. It literally goes around the outside. And your row decoder and your sense amp area grows about the square root of the array, because each of them is kind of along one side. There's a little bit of fixed overhead that's just control circuitry that even a little RAM needs, and a big RAM needs it too. What is that control circuitry? So a RAM is actually a very interesting block to build. So if you, in one of your design courses if you have taken any courses where you're building custom hardware, a RAM's an interesting challenge. Because to make it work and to be fast, there's all sorts of self-timed circuits in it. What that means is the clock hits and the RAM basically says, okay, I want to wait this long, and then I can activate the word line because the decoder's done. I wait a little bit longer, and I basically pre-charge the bit lines. I wait a little longer, and I activate the sense amp. So there's all sorts of timing signals that are happening. Like the core of the RAM is actually analog. Its interface is digital, but inside it's analog, and you've got precisely timed signals. That takes this C3. That's like where that area comes from. And then this last term is proportional to how many things we're connecting to the programmable routing. Because programmable routing is expensive, so just like the logic blocks, we have to look at how many inputs and outputs we have, and it's going to take some area to do that. So that's unique to FPGA block RAMs. Okay, so that's our cost function. If we make big RAMs, our cost per bit is minimized, right? Because we kind of amortize all this other stuff. But if we make really big RAMs, there's a higher chance of wasting a lot of it. Because if we have a lot of little logical RAMs, we're just going to wind up mapping them to big physical RAMs, and they waste most of it. So they might want a small RAM. Another thing they might want is maybe they want a lot of bits, but they need a wide data word. Okay, so they need maybe, I don't know, 64 kilobits, but they need a data word that's 512 bits wide. That also doesn't fit into most big RAMs. Like, data words are also expensive. The wider I make my data word, the more of these route ports I have. So it's expensive to make my physical RAMs have really wide data words. And if I have a big RAM, but it needs a very wide data word, my physical RAMs only have narrow data words, well, I still need a lot of physical RAMs. Okay, so it's another constraint. Yeah.
Small RAMs like what? For free. Won't pay any extra overhead by stacking up parallel. So if you would err on the side of small RAM, save as many as you want to build up triple wide.
You can. So, but basically, this is a classic trade-off. So it's why it's worth it exploring with CAD tools. If you need big RAMs, it's better to have big physical RAMs, but there's also a big chance of wasting them if you need, like, you know, either a really wide data words or a lot of small RAMs. So what should you build? And it's basically unclear. You actually have two competing trends, so you can't really just say go this way or go that way. Probably the best answer is going to be usually in somewhere in the middle. The last thing that FPGA RAMs generally do is, okay, so we're building these physical RAMs, and when you build a normal RAM, it would be something like 512 words by 16 bits, right? So a word is 16 bits, there are 512 of them. So what you build on the FPGA, the RAM might be, for example, 1,000 words and 8 bits wide. But you don't know how people are going to use it, right? Some people might use it that way, but some people might want to have, for example, 8,000 words and 1 bit wide. And maybe that's not wide enough, but you could put a bunch of them in parallel if they needed 8,000 words, and you could make them a bigger word width by kind of putting a bunch of physical RAMs in parallel. So it turns out that all you need to make a RAM that really is 1,000 words by 8 bits, behave as if it was any one of these other organizations, is a few extra multiplexers. So most FPGAs, they put those extra multiplexers right in the block RAM as hard logic, so that the RAM has basically a configurable aspect ratio. It can be kind of a bit tall and thin or a bit short and fat. It adds very little area to the RAM, and it makes it usable by more people without soft logic. So that's what the vast majority of FPGA block RAMs do. And in assignment 2 or assignment 3, we're assuming that as well. Okay, does that make sense? I'm going to take that as yes. Okay, so this is a complicated picture. You don't have to understand it all. It's taken from a paper by Kosuke Tatsumura, if you want to look it up. This is basically what I just showed you, right? This is the core of our RAM with all the regular circuitry, and then FPGAs add some stuff around it. So what do they add around it? First, they add routing ports. So we have input routing ports, and we have output routing ports. We have registers on all our inputs. So I told you that RAMs nowadays have all these self-timed circuits, right? Like I need a certain amount of time to pre-charge the bit lines, a certain amount of time for sense amp. It turns out to be almost impossible to design those if you just say people can activate the RAM at any arbitrary point. If you basically say all the inputs have to be registered, it's much easier to build the RAM, because you can say everything starts at a clock edge, and I build circuits that will produce pulses that are a lot, some amount of time after that clock edge to control various things. So this is why when you use a block RAM, and you may have found this in assignment too, like you have to use input registers. It's not legal to say, I don't want the registers, just do it combinationally. Nobody can, if you actually go back long enough, like 20 years ago, 30 years ago, actually 20 years ago, people would build RAMs that way. As they got faster, it just became impossible. So RAMs, block RAMs have to register their inputs, okay? And then the last thing is the details of this don't matter too much. This is showing how it's a one way of implementing it. This is basically some extra muxing that implements that configurable width. So the RAM itself here would output, for example, let's say, I don't know, a 16-bit word. This muxing would allow you to directly send out that 16-bit word or pretend it was 4-bit words by doing a little bit more muxing to figure out which 4 bits within the word the person actually asked for. If they didn't want a 16-bit word, they wanted, instead of 1,000 words, they wanted 4,000, but only 4 bits wide. This muxing would make that happen, okay? And that's all included in the area model I've given you. Any questions so far? You're all with me. Okay, so I'm going to take that. I think you're with me. I'm going for it. Okay, so that's another thing we need to think about is how expensive are routing ports. So we've been talking about how expensive are the bits. What other circuitry is coming along for the ride? So what's the area model? So another decision we have to make is how many ports do we build in our physical RAMs? And that's basically a decision of how much will they get used and how much do they get cost. So the simplest RAM we could possibly build is here. It's a single read-write port. So it's got one address and it's got one bus that is both read and write. And at least that's the way you think of it. See if I animate this in. You can't really build a bus that's both read and write on an FPGA. So what you really build is a single address input, and you build a read data output and a write data input. We can't really have like a port that flips back and forth, right? It's not efficient to build that anymore. So a single port RAM, this is what you actually build. One address, you'll have one read data output, one write data input. What can you use this for? You could use it for program memory, for constants, basically things that aren't going to change. And the cost of it is 6 transistors per bit, because we can use that single port RAM cell. And then when we think about routing ports, we need to send in the address. We need to send in the write data. So we have address bits plus width, whatever the data width of the RAM is, the maximum data word size, input ports, and then we have to send out the read data, which means we have whatever the maximum width. If the word maximum is 16 bits, we have 16 bits of output ports. Okay, so that's kind of what it costs us. And yeah, this is what it's useful for, like only things that aren't going to change while we're running. Does everybody get that? Because otherwise the other ones are going to be complicated. Okay, so that's the simplest RAM we can build. We can make it a little more complicated. We can make a simple, what FPGAs call simple dual port. That means one read and one write port. And I've shown that over here. Okay, so we've got a read address now and a write address. We've got a read data and a write data. And the first thing you notice is that, well, it's not that different in terms of routing ports. Like before, even with a single port RAM, we still needed a read data and a write data. So the only thing that we've had to add from the outside connectivity perspective is like a write address set of inputs. So it's not much. What do we need it for? So FIFOs. So FIFOs fundamentally want a read and a write. FIFOs are very common in FPGAs. What's the cost? Okay, so we need to use a dual port RAM cell. So it goes from 6 transistors to 8. And then in routing ports, not many more. We need two address inputs. We still need one write path. So that's like our data width. And we still need one read path, which is our data width again. So if we compare these two, there's some extra cost. We went from 6 transistors to 8, and we added a few routing ports, but it's not that bad. So this is pretty dominant in FPGAs. There's so many of these in FPGA designs that every FPGA at least builds simple dual port in its block RAMs. Okay, so if we want to go a little further, we could say, let's make 2 read-write ports. Okay, so what does that mean? So this could be useful in things like processor caches, memories that are kind of essentially modified in more random ways. Like sometimes you might read them a lot, sometimes you might write them a lot. What does it cost? We already had a dual port SRAM, so it doesn't change the SRAM cell. All it changes is basically how many inputs and outputs we have to the programmable routing. So we basically need to have a separate read and write bus for each of our 2 ports now, because we don't, in one cycle we might send in 2 write words, and another cycle we might send out 2 read words. So we wind up with more input and output routing ports. That's the basic cost of this true dual port. The RAM itself doesn't really change. We just wind up with more signals going to the programmable routing, which does cost us area. Okay, and then you can go further, right? So you could go to 2 reads and 2 writes, and that's called simple quad port. Quad because it's 4, simple because some of them are dedicated read and some of them are dedicated write. If I did that, what's it useful for? Register files. When you build processors, they like to have lots of ports on their register files. If you actually look inside a high performance like Intel or AMD processor, the register file would have a huge number of ports, okay? Shared memory switches. So there's a lot of packet switching that you do in FPGAs. One way you can do switching is everybody writes into a memory. Like all the incoming data gets written into memories, and then you read it out to whatever output ports need it. So you can have a shared memory switch if you have a lot of things writing data into it and a lot of things reading out, and everybody can read and write random addresses. It forms a switching function that can be quite useful in packet processing. And the more ports you have, the more powerful that switching function becomes. So it's useful for those things, but it's expensive, right? So we need to actually, to do 4 ports like this, we need to go to 12 transistors per bit, and we need to add a bunch more routing ports. So it does get expensive. Altera did do 1 chip with quad port memory called Mercury. How many people have ever heard of Mercury? Yeah, it was a bad idea. Okay, so it happened before I joined Altera, but there's experimental proof that there's not enough demand for this. Okay, so don't do it. It's beyond the sweet spot. So it costs a bunch extra in your physical RAM, and there's just not enough use cases. There are some, but not enough. Yeah. I'd have to go off and think about it. Like you can think of all the functional units you have, which is a lot, right? If you look at like a high-end processor from Intel or AMD, like the number is constantly changing, but they may have like 10 different functional units that can be accessing the register file. Each of them might be grabbing 2 operands from the register file. So, to first order like that, I just made a 20-ported register file, right? Oh, and then I can also have a lot of things writing back. Now, they probably use all sorts of tricks. Like, are there ways that we can we do any partitioning of the register file, et cetera? We saw one of the DSP processors did that. It's hard for Intel or AMD to do that because they can't do anything that's kind of visible to the programmer because their instruction set was set long ago. But yeah, basically they can easily get up into like 20, 30 ports. They can get up into those kind of numbers. Yeah, and they could do that. So I mean, they probably do that some. They probably do choose, like, I mean, those processors are finely crafted pieces of engineering where a huge team of people has sweated over every picosecond. So you're probably right. They probably have actually duplicated the register file in various places, and there's probably a ton of micro optimization that's gone into that. So anyway, so this gets expensive. Now there is, okay, so I told you that Mercury, an Altera chip, did this. It was a bad idea. If you actually go look at the data sheets, you won't find this in AMD. I went and looked for AMD, and AMD basically stops here. Okay, this is as far as their physical RAMs go. They can do true dual port. Okay, and that's also true of most Intel FPGAs. But two of the recent ones, Stratix 10 and Agilex, will actually support this in the actual physical RAMs. So not just they're mapping it for you behind your back, if the physical RAMs can do it. They haven't published this, but if you look at their data sheet, you can tell that what they're actually doing is they've really built this, okay? But they have hard time domain multiplexing circuitry. So they can time domain multiplex and basically slow the RAM down. So a RAM that normally runs at a gigahertz for all of these earlier modes, because that's what you get in Agilex or Stratix 10, suddenly drops down to 600 megahertz if you use this mode. And what that's saying is this mode is not really there. What they have is they have time domain multiplexing circuitry that actually does two of these axes. Okay, so it's basically doing 2 reads, 2 writes using a simple dual port RAM. It's not quite twice as slow because maybe there was a little bit of overhead before, but it's almost twice as slow, but it's still pretty fast, right? If your design's running at 600 megahertz or less, it works pretty well. So yeah, that would be one of the examples where there's a vendor that's put hard time domain multiplexing circuitry in to give you a slower but more highly ported memory. If they didn't do that, you can always do it yourself, but it is, as Isidore said, it's a bit tricky, right? You're putting soft logic around this RAM and it's got a close timing at a gigahertz, so it's going to be a bit tricky. Is everybody with me on this? So what most FPGAs do is they build true dual port. Okay, so they go down to this level. Okay, because they really need this. Okay, so I told you Mercury was a mistake where it actually built real quad port memory, didn't time to multiplex it, was too expensive. It would also be an enormous mistake to go here. Like if you made an FPGA, you say, I only have single port RAM, I can't do FIFOs. That was probably a career decision, right? Like you just burnt through $200 million of venture capital, and like you're going to have a very embarrassing debrief of like, why did you do this? So your interesting region is basically here. Okay, you're going to do one of those two things. Yeah. 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 So I'm going to talk about that on the next slide. So basically, this is dominant. You're going to find like in the assignment 2 benchmarks, or assignment 3, sorry, I'm merging all the assignments into one Uber assignment. So the assignment 3 benchmarks are real. So I actually got them from the Stratix 5 architecture effort. So those were actually the exact same ones that were used to architect Stratix 5. And what you'll find is that about 80% of the RAMs are simple dual port. Maybe 10% are true dual port and 10% are single port. Okay, so simple dual port's the most common mode, but true dual port is non-negligible. Now, true dual port, what does it cost you? It costs you basically these extra routing ports. That's actually what makes it expensive. So what most vendors do is because the RAM core you build is pretty much the same for true dual port and simple dual port, you can expose that this really can do true dual port, and then just limit how wide it can be. Okay, so let's see if this is understandable. Yeah, so the cost is basically more routing ports. What almost all vendors do then is you basically just say, when you use it in true dual port mode, you can't make your data word as wide. Okay, if you can't make your data word as wide, if we limit it to half the normal maximum data word, then you'll actually fit within the input and output port counts that we already built for simple dual port. So you get all the modes except that widest one without really any extra cost. To give you that last widest one, a whole bunch of routing ports would have to be added. That's not a good idea, so they just forbid that mode. Does that make sense? So that's why you get that constraint, and why that constraint shows up. It'll look somewhat random, but you'll see it in all sorts of FPGA data sheets because they're all doing the same trick, right? We'll just forbid that mode and we don't have to build more routing ports. Okay, and yeah, from the point of view of what this means to an end user, if your maximum data word size that you kind of built enough routing ports was 32, you can use that in single port, you can use that in simple dual port. When you go to true dual port, it basically gets halved. You go, okay, you can only use it up to 16 because you actually now need 2 read inputs and 2 write inputs. We're not going to build you anymore. So you just got to divide this 32 up across those 2. And from the end user's point of view, that just means you can't use that extra wide width. Does that answer your question, Isidore? So yeah, and that is a constraint that you have. in assignment 3. Okay, so next thing, that was all about block RAM. Like how are you using these and also what's inside them? Let's talk about LUT RAM. So a 6 LUT is a 64 deep, 1-bit wide ROM. So 64 words, each 1 bit wide. And 4 LUTs used to be dominant, but now 6 LUTs are. So it actually makes LUT RAM more appealing because a 6 LUT has a lot more RAM in it, right? It's 4 times as deep. So if we could write to this, we could use it as a RAM. I mean, a LUT is a ROM. If we could just write to it, we've got a RAM. So is it worthwhile? So whether it's worthwhile or not depends on how much area we have to add to it. But if we can keep it cheap, maybe it's a good idea. Okay, so let's look at what do we need to do if it's a RAM. Okay, so here's a 6 LUT. And it's fundamentally a 64-word, 1-bit wide RAM. Every architecture that uses 6 LUTs now uses fracturable 6 LUTs. So it can also be 2 5 LUTs. 2 5 LUTs is 32 words deep and 2 bits wide. So we actually get 2 different modes kind of for free. Like that's what we already built. The read path is already there. That's how we use it as a lookup table. But we need to add write circuitry because the write circuitry for a normal LUT is just the configuration circuitry. It's like load everything in, like my 100 million bits and my LUTs will be configured. I can't use that in my design. I need to have a write path. Okay, so what do I need to do to add a write path? So I need to have an address of what word am I trying to write. So for a 6 LUT, that's 6 bits. I also need to have a data bit. What am I actually trying to write into it? So that's 7 bits. And I already have 6 inputs that are used for my read address. That's my normal LUT inputs. So if I add this up, I just basically said, well, let's just add all these routing ports to my lookup table. I wind up with 13 routing ports. If I redo this for the dual 5 LUT mode, it's a little better, but it's 12 routing ports. So that's pretty bad. Xilinx builds, AMD builds 7 routing ports to their 6 LUT. Intel builds 8, which is a lot less than 13 and 12. Okay, so nobody's got enough routing ports and it's expensive. You're not going to do this. It's going to make your LUT, 50% more expensive. You're not going to do this. Okay, but despite that, LUT RAM exists. So what do they do instead? Yeah, what do you think, Isidore? So you could do that. Any other thoughts? What do you think? You could. Okay, so you're saying like maybe make it 4 bits, but then I can only use 16-bit deep RAMs. So you could do that. There's a more powerful one though. Right now this LUT, I'm basically giving a write address to every LUT. I can just say, well, you're not allowed to use them as 1-bit wide memories. I'm going to say you have to use them together. So I'm going to lock the write address together. And what that's going to do is basically say you can't have a whole bunch of independent 1-bit wide memories, but that's kind of bizarre anyway, and would actually fit in registers reasonably well. So I'm going to force you to use them in somewhat wider modes, but then I can basically broadcast the right address. And that's what the technique they use. Okay, so what Intel does is they basically convert an entire logic block. So if you stop thinking about this as one LUT turns into LUT RAM, you say the whole logic block has to together turn into LUT RAM. Then what you can do is say, well, I'll share the right address across the whole logic block. Okay, I don't need to have a different write address for every single LUT. I do need different write data for every LUT because it would be bizarre to say like you can write all 1s or all 0s in your words, but you can't store the number 3. Like that would be odd, right? So you do, but what do I need? I need basically to get 6 bits of address, and I need to get write data for every single LUT. So if I look at the ALM, it's got 8 inputs. I use 6 of them for the read address. I can use 1 for the write data input, and I can take 1 of them and get 1 bit of write address. If I do this for all 10 ALMs, I have more than enough to get all 6 bits of write address, as long as I now consider that write address is for everybody. So you kind of put it together. If I do the same analysis for the 5 LUT mode, it also works, right? I have 3 inputs left over. I need 2 write data inputs, and I've still got 1 left to contribute to the general pool of write address. Okay, so by doing this, the cost is kept a lot lower, And the constraint is just that you have to use the whole logic block as LUT RAM or none, which is not too bad. It means my RAM is fundamentally going to do 10-bit data words or 20-bit data words, but it can't do 6-bit, it can't do 12-bit. You have to round off. Okay, this I kind of told you all of this, so I don't think I need to repeat that. And I guess what I'm emphasizing with this reuse and reuse costs is one of the ways you try to make an FPGA more efficient is think of, I already have this circuitry, can I use it for other stuff? But don't add much to it. Okay, are there clever tricks? So LUTRAM is like that. It's a clever trick to reuse what you already have. So how much better is this? LUTRAM is about 30 times more efficient than building RAM from registers if you wanted every bit that's in the LUTRAM. So they're perfectly matched. You get a very good win. If it didn't perfectly match, it'll be somewhat less. Xilinx uses a similar but not exactly the same trick. So they only have 7 inputs to their 6 LUT. So they use 6 for the LUT and they use 1 for the register, but they get basically 7 inputs. So they've used 6 of them for the read address. That's your normal read path. They got 1 left for write data. If you think of that, when they use it as 2 5 LUTs, they use 5 of them for the read address, and they got 2 left for their 2 write data. But they got nothing left. They can't steal anything for the write address. Okay, there's nothing left to contribute to some write address. So what they do is essentially what Isidore suggested. Well, so if Isidore, so what would you do? Maybe Isidore knows this, or maybe he doesn't. But Alex, what do you think? I'm not sure if I know what does that mean? You need the right address, though. I need to be able to say which word I wrote to. Do you know what I mean? So right now, if I don't have a right address and I send you like not having a right enable, not having a right address is kind of like a random number generator, right? So like I'm writing something, I don't know when and I don't know where. So I do need to get a right address. But yeah, so what would you do? Xilinx does something that's slightly different, but is also clever. Okay, so I'll tell you. So what they do is, okay, so if it's a single port RAM, they just basically say the read address and the write address are the same. Okay, they'll just route they have some write address circuitry, they'll just reuse the read address and it works fine. So they can convert their logic block to a RAM. But single port RAMs are only about 10% of the FPGA RAMs. So you'd really like to do at least simple dual port. So what they do for simple dual port is they just say, well, we're going to steal 1 LUT. 1 LUT becomes unusable. Okay, they'll convert the whole logic block, but 1 LUT, they stole all of its read inputs, so you can't use it, but those are all contributed to the pool to become a write address. So if you look in their data sheets, you'll see these odd numbers like that they can do like a 64 word by 7 wide simple dual port RAM and a logic block. The reason it's by 7 is the logic block has 8 things in it, and one of them had all its inputs stolen. And if they use the 5 LUT mode, you'll see it's 32 words and by 14 when there are 8 things there. So one of them's gone to contribute the addresses. This is also a good solution. Okay, so how do you put these things together? So, well, you're doing this for assignment 3. You're exploring this space to figure out what's the best trade-off. And a big part of that is on an architecture that's very similar to the StratExplore memory architecture. That architecture has 50% of the labs support LUT RAM, and it has 2 kinds of RAM, 9 kilobits and 144 kilobits. So yeah, so the architecture you're doing is quite close to that. It's pretty realistic. Let's just to get a sense of how the trade-off space, these are data on how much area a couple of different logical RAMs would take to map to different solutions. Okay, so I'm going to start with a large logical RAM. Okay, so I've got 2048 words, 70, and each word is 72 bits wide. So this is a big RAM, right? I might use this for storing part of my packet storage or a program or something, like, but it's pretty big. And I need 1 read and 1 write port. So this perfectly fits on purpose the big RAM in StratExplore. Okay, so like you're never going to find a better case for it. Like this is as good as it gets. It's a perfect fit. And using like the published area data on how big because this I chose StratExplorer because, as I said, the data is published. How big are the various RAMs and the logic block and so on. So we can actually work out silicon area. So if I use a 144 kilobit RAM, I don't need any logic. It perfectly fits. I just need one of these big RAMs. And the silicon area is 1 and the F max is 336 megahertz. So the silicon area is like 0.22 millimeters, but we'll just define that to be 1. And the F max is 336 megahertz. We'll define that to be 1. Okay, so let's say we map it instead to 9 kilobit RAMs, the other RAM that exists on this chip. We need 18 of them. We don't need any logic because we actually just combining them all in parallel to make a big enough word. These RAMs can implement 2K words. They just aren't wide enough, so we'll put a bunch of them in parallel. Its area is almost twice as big. Its frequency is actually better. Like it actually runs at almost 500 megahertz. So the reason is physically this big RAM, some of the internal wiring inside the RAM actually gets larger, right? So the bit lines get longer, et cetera. So this larger RAM actually is slower. And it turns out that putting a bunch of small RAMs in parallel is actually faster. And that is a realistic thing that happens sometimes. Sometimes we also screwed up the design of certain RAMs. So we might have been able to do a bit better than this, but this is real data. That's what happened. Okay, so we can map it to LUT RAM. This is a pretty big RAM, so we don't think this is probably the most logical thing to do. It takes 3,300 ALMs. So it's 12 times the silicon area, and it runs a lot slower, 40% of the speed. Okay, so you can map it to LUT RAMs, but it's quite a bit less efficient. And we could map it to registers, and that's really inefficient. 313 times bigger, also 40% of the speed. Okay, so what's the point of this? I mean, big logical RAMs, it fits okay in a medium-sized block RAM. Like it's not terrible, but it is less efficient. Doesn't fit LUT RAM very well, and putting it directly in registers is catastrophic. But obviously, this isn't the only size of RAM that a person makes. This logical RAM is pretty big. So if we do this again, but now for a smaller RAM, so 1,000 words by 8 bits wide, and you map it to different things, well, it still takes an entire 144 kilobit RAM. Okay, so it gets the same area. If we put it in the smaller 9 kilobit RAMs, it only needs one of those. It's a perfect fit. It's actually only 10% of the size. So this shows you why you don't want to make just all big RAMs. Like for this RAM, the big RAM was very inefficient. If we map it to LUT RAM, it took 216 ALMs, and the area was better than the big RAM, but 8 times worse than the sort of smaller medium block RAM. Yeah, so basically this kind of defines some of the boundaries of the space, right? You can't take this and say this is exactly what I should build, but hopefully it shows you why you need to pay attention to whether these are asking for, because there are big trade-offs in this space. Okay, so in this paper, you can go read if you want, but I haven't assigned it because there's too many papers to read otherwise. They go off and do a bunch of studies about block RAM size and efficiency as part of the Stratix 5 architecture. And this, again, is similar to what you're doing in assignment 3. Okay, so what they're showing here is what's the total area of the chip? How many logic blocks do they have per RAM block? So as I move this way, I'm basically getting more RAM blocks on the chip. And then they do a few different studies. They say, what if we just build a 40 kilobit RAM? So you got one type of block RAM. If you do that, the area is up here. It's not the best. And if you did that, you should have not too many of those RAM blocks. They also do basically the Stratix 4 style. That's this, let's see, that's this line. So the Stratix 4 style is a mix of, actually it's this one. This is the Stratix 4 style. So it's a mix of 10 kilobit and 144 kilobit block RAMs. So it's 2 different sizes, one big, one medium, and it works pretty well. And then they also looked at what if we just do a single RAM that is, that is 20 kilobits. And that's this pink line. And they find that works just about as well. Okay? And they have to tune it, like they have to decide how many RAM blocks to build. Like you notice that the minimums on these curves aren't all at the same place. So depending on how big your RAM blocks are, you might need more or less of them. But the conclusion from this is a 20 kilobit RAM, if you properly choose all the parameters, works pretty well. It works just as well as a mix of 10 kilobit and 144 kilobit. So they decided to switch to that because it was simpler, right? They only need to design one RAM block. It's easier for the CAD tools. And the other thing that they liked is that it was easier to put a 20 kilobit RAM was actually friendly to putting ECC in. So for high reliability customers, they worry about soft errors due to radiation. If you have, these block RAMs added error correction circuitry. If you store some extra data as parity bits, they can basically fix soft errors. So for that reason, Stratix 5 switched to this. The reason I'm showing you this is, well, it's interesting, and it's also hopefully gives you some ideas for some of the trends that you might see in assignment 3, right? If you see wildly different trends, well, then your mapper might be doing wildly different things. So, yeah. Yeah. So the reason they have like M9K and so on is that its fundamental mode is kind of like 8 bits plus 1 bit parity. Okay, and that's why you got like 9-bit, 18-bit, 36-bit wide rather than 8, 16, 32. And then when they went to 20 kilobits, its fundamental mode is like 10 bits wide, 20 bits wide, et cetera, because they didn't want just one parity bit. They wanted enough that they could do error correction. Now, lots of people don't do error correction and don't have parity bits. But because you've got all these logical RAMs anyway, somebody sends you in a RAM that's 512 bits wide, you just chop it up into the pieces that fit the things. So in the end, the parity bits sometimes don't really matter. You're just dividing some wide memory instead of by 8, you're dividing it by like 9. The intuition behind putting it in was that there are people who want parity bits. If it had all been done at 8, I'm not sure it really would have mattered much. For the 20 kilobit, because there is actually hard error correction circuitry in it that you can turn on, it does work better if it's like 20 or 40 bits, because you basically need, well, like on a 36-bit word, it turns out 4 extra bits is enough to do error correction. Does that make sense? And then for anybody who doesn't want error correction, which is probably still most of them, you just take whatever width they wanted. Instead of dividing by 36, you divide by 40 to figure out how many block RAMs you need. And it still works out pretty well. So yes, good question. Thank you. Okay, so see if there are, okay, so this is a busy plot from Principles and Practice survey paper. It kind of just shows for Intel what has been the evolution of their block RAM architecture. The Xilinger's trend is similar but somewhat different. So they make different choices, but there's a few interesting things here. So you start off with like relatively small block RAMs, like 2 kilobits. And then there have been trends where they sometimes split into, let's have this chip actually had 3 different kinds of RAM, then 2 different kinds of RAM in Stratix 4, then Stratix 5 and beyond are back to 1 kind of RAM. Most recent chips put in a really big one again. So you often see mixes of RAM sizes, but then sometimes they converge to one in the middle. So there's no general agreement on that. This is basically how big the chip is in terms of logic capacity. So as time goes on, we've been going to more and more advanced chips. And the vertical axis is how many bits of memory you have per logic element. And basically it's been going up. So that memory has been getting more and more important. Okay, so there's been a long-term trend of FPGAs are getting more memory rich. You have more bits of memory for every logic element. The block RAMs have sort of been getting bigger, but it's been chaotic, right? So there's no general agreement on what the best way to do this is. Basically, partway through this, LUT RAM was introduced, and that's part of why the smallest RAMs kind of tended to go away. LUT RAM is actually pretty good at doing the really small RAMs. So in a way, the architecture has gotten even more memory rich than this shows, because there's a dividing line here of the earlier architectures didn't have LUT RAM, the later ones do. So there's some more RAM bits that you can make out of logic on the right-hand side that you didn't have on the left. And if you want to figure out what all these are, you can ponder all the symbols. So, okay, so that was Intel. What about AMD? At a high level, it's similar. It's more similar than different. But if we take Vertex, Ultrascale, and Versal is basically the same as this. Their fundamental RAM block is 18 kilobit, and it's also configurable. So you can make 18,000 words by 1 bit, or you can make 512 words by 36 bits. And various options in between that. So it has this configurable muxing. And they do the same trick of if you use true dual port mode, you can't use 36-bit wide words, you max out at 18. And it's because they don't want to build all the extra routing ports, same trick. They build a little bit of extra hard circuitry. So they build hard circuitry that allows them to basically combine two 18 kilobit RAMs into one 32 kilobit RAM. So a lot of their literature describes their RAM block as 32 kilobits. It isn't really, it's 18 with some hardened muxes so that you can combine two 18s into one 32 basically seamlessly. You don't need any soft logic. And in their most recent chips, they've also added a really big one, 288 kilobit RAM. And that one, they probably bought the RAM core. Big RAMs get harder to design, so it doesn't have, I mean, I'm guessing this, but I know I saw things like this inside Altera too. Usually when we had a RAM that wasn't configurable, it's because we bought it from a memory vendor. Like we bought the IP and put it in, and nobody except FPGAs wants configurable width, so you just didn't have it. So that's a guess, but that would be my guess as to why that one doesn't have configurable width. And in Xilinx devices, it's the same trend. There's been a gradually increasing memory bits per LUT. Okay. This is further reading. I'll let you think about it. There's a paper on how if you're curious, how would you map to RAMs to minimize power? That's what the first paper does. There are papers on like, what if we don't use SRAM? So this paper is on what if you use magnetic tunnel junctions as your SRAM store instead of SRAM? You can make it work. Your block RAMs get denser, but they do get slower to write. If you're curious, you can go read these. Maybe they'll go into your term paper. That's it for RAMs. Any questions on that? Yeah. I mean, you can still do the configurability in soft logic. So let's say that I actually didn't need a 72-bit wide word. I needed 36. I mean, I can build that out of soft logic. So, and for a RAM that big, the amount of soft logic you're using is probably pretty amortized. So it's not catastrophic. Does that make sense? But it does undercut my argument about configurable RAMs. So I just like it for that reason. So yeah. If you have a very specific question about it though, we should probably talk about it after. I think you're asking about the assignment, or what do you mean? I think maybe that one I'll take offline. If it's a question about how to do the assignment one, is it about this table or is it something else? I mean, in this one, it's just what do they use? So this is just this one logical RAM by itself. What do you need to implement it? That's what this is, which is a little different than the area calculation in the assignment. In the assignment, you're always calculating. This is something that some people trip up on. Post on Piazza if you're confused. You are calculating the area of the chip. The chip, an FPGA architect decides you get this much logic for this much RAM. If your mapper decides, I don't care what you built on the chip, I just love using this kind of RAM. Like that's the only thing I use. There's all this other stuff that's unused, but I don't care. Well, you pay the cost of that. Okay. So when your area calculation is the area of the chip, not the area of what you use. So if you just use, so you're trying to do two things in your RAM mapper from an optimization point of view. Basically what this chart shows you is if you take like a little RAM and you map it to a little logical RAM, you map it to a big physical RAM, it's not that efficient, right? In silicon area, it's not a great fit. And vice versa. Take like a large logical RAM, map it to a whole bunch of little LUT RAMs, pretty inefficient. So that's one thing you're trying to avoid, right? The other thing you're trying to do is there's a fixed ratio of how much of each thing you have on the chip. So if you've used up all the big RAMs, even if it's not the best solution to map this next logical RAM to the medium ones or the LUT RAM, if you got a lot of that left on the chip and no big RAMs, it's still better. So you're kind of doing two things. Try to find an efficient solution for each logical RAM, but also pay attention to what's left over. And those two things are a little bit, you have to balance them, right? There are lots of different ways you can balance them. But to get a good mapper, you need to think about both of those things. Does that make sense? It's a big hint. So, and there's lots of different algorithmic ways you could do that. All right, so I have 4 minutes, not 6 minutes. I'm going to use them. Okay, so I'm going to see how far I can go on this. We'll keep going next week. Okay, so I want to talk a bit about multipliers and other hard blocks. We talked a bunch about logic blocks, then RAMs. So let's talk about more specific hard blocks. The way you evaluate how to do that is, yes, you're empirical. So you have some idea, like maybe I should harden PCI Express. And all FPGAs pretty much harden this now, but that wasn't always true. So there was studies like this done to decide should you do that or not. And the way that that's done is you basically develop the soft IP. So you can do this without any new hard blocks. You just use the current RAM and logic and so on. So you develop that IP. And you can basically instantiate that IP in different ways. One of the nice things about the soft IP is there are multiple, let's take PCI Express. There are multiple generations, multiple configurations. Your soft IP is always going to do just only what the person needs. If you ask for Gen 2, you'll get Gen 2. If you ask for by 8, you'll get by 8. Like any feature you don't need, it won't build. So you take that IP, you can work out its area, speed, and power. You have to estimate how often it's used, and you have to compare it to the hard IP. So when you create the hard IP, you typically start from your soft IP. You already have that normally because you wouldn't be considering hardening this if it wasn't already important. So you have soft IP for it. But that when you create the hard IP, you can't say, well, I've got all these different variations like Gen 1, Gen 2, Gen 3, and I'll use whichever one's appropriate. Your hard IP has to do them all. So usually you wind up essentially taking the superset of everything that's used in the soft IP. You harden all of that. So for PCI Express, I might have the first 3 generations and a big mux choosing which one to use. And I might be able to get more clever, right? I might say, well, there's some commonality in these things, so I'll factor that out, and I don't need to make 3 copies. But you're going to get some bloat because of that. But then you're going to get a big reduction because of the fact that you're not using soft logic and soft routing, like the configurable logic and routing. You're going to use actual ASIC standard cells and metal. So you get a big win from that. You have to connect this to the rest of your design. So you have to add the routing ports back in, right? Usually you get a much bigger win until you add the routing ports so you can connect to everything else. And now you basically have your 2 cases. And you have to estimate, well, how often is this going to be used, and is it a net win or not? Okay, so that's the basic flow for how you should evaluate hard IP. Let's see. Actually, I'll ask you one question. So this used to be done primarily for area. Okay, area was the biggest win for hardening something. Because we saw if you're using mostly logic and programmable routing, you might get 25x reduction in area. If you're by hardening the whole thing. If you're using a lot of RAM and so on, then it was smaller. But everybody who didn't use it just paid that dead weight, right? You harden something, everybody who doesn't use it, their chip just got a bit bigger and they get no value. Okay, so increasingly power is a big factor. So what do you think? Does power make you want to harden more stuff or less stuff? Or it doesn't matter, just do area and it's fine. What do you think? Yeah, so you think... So that's basically, yeah, okay, so I think you're saying it depends on your market, you'll care more about area or power, but let's just say that let's say that I've decided that people used to care about area, but now they care more about power than area. So I've made that decision because I like making arbitrary decisions. And that to a large extent, that is happening. Do you think that makes you want to harden more things than back when you were evaluating this trade-off for area, or does it make you want to harden less stuff? What do you think, Isidore? Yeah, so it actually does make the case for hardening simpler. The case on area was, okay, I hardened this thing and I got I don't know, it depends on exactly how it all worked out, but maybe I got a 5x area gain, maybe I got a 10x area gain. Those kind of gains were possible. But if only 10% of my customers used it, it's still a wash, right? I got a 10x area gain, 10% of the people used it. It's actually not worth doing because everybody else pays that penalty, right? So the expected area reduction is actually 0, right? 90% of my customers take a 10% area hit. 10% of them get like a 10x improvement, roughly a wash. Power is actually more beneficial because you get a power reduction that's to first order proportional to area. So I can get a power reduction also of say 10x. And if I use it, now I get that power reduction. If I don't use it, my dynamic power is proportional to switching rate. So I basically, if as long as I don't have this thing switching, which if I'm a competent designer, that should happen. Doesn't always happen actually, but if I'm a competent designer, it shouldn't switch when you're not using it, which means my dynamic power goes to approximately 0 when I don't use it, and it's 10 times lower when I do. So the trade-off's actually more favorable. And if it was all about power, then you'd actually harden tons of stuff, but it isn't. You still have to care about area too. Static power is slightly more complicated. Okay, so if you make the thing 10 times smaller, you also are reducing. It's always there. Okay, so everybody pays that static power, so it's closer to area, but you probably have an idea about that one. So yeah, so if you don't do any power gating, the static power trade-off is similar to area, right? You got a big win if you needed it, because you got a smaller chip. You got a loss if you don't need it because it's sitting there leaking, you don't use it. But you can power gate it. So does everybody know what power gating is? Right? You put another transistor between the power rail and all your logic, it cuts your leakage massively. So if this is a hard block, typically it's fast enough, it has some headroom. So power gating something costs you typically around 10% speed, but you probably can tolerate that because you just hardened the thing. You put a power gating transistor in there, and now the CAD tool just configures that to be off, and now it doesn't leak static power either, or significant static power when you don't use it. So the power trade-off actually favors more aggressive hardening. So I think it's an interesting trend. It basically makes FPGAs more heterogeneous, more diverse, because it's beneficial if a fair number of people will use this to harden it. And you can see that the chips are getting more heterogeneous. And I think that's about all the time I have now. So I have lots more stuff on getting into DSP blocks and so on, but we'll leave that for next week. Okay, thanks everybody.